All right, today we're going to be doing Lewis dot diagrams. And so, what Lewis dot diagrams are is just a simple diagram that shows the number of valence electrons, and we represent them as dots around the symbol. This will end up being real big when we start doing reactions and bonding, and we represent all of our different atoms and elements this way to see how they're going to bond. Um, but in this, we use that word valence electrons. And so first, let's define that. So valence electrons are going to be the electrons in that outermost energy level. So if we look at a simple Bohr model of the atom here with our rings, we can see, well, in this outermost shell, the outermost energy level, there are these two electrons. Those would be valence electrons. Everything below that would be core electrons, and they're in orbitals that are totally full, and because they're inside, don't react. And so we're only focused on what's on the outside. Now you might ask, how do we know? And so what we do is we look at the periodic table, because the number of valence electrons is going to correspond with the group number. All right. If we look at this right here, we have group 1, and then group 2, specifically 2A, 1A, 3A, 4A, 5, 6, 7, and 8. All right, we're going to skip over this middle section and not talk about the bottom sections. They're going to be complicated. And so we're going to focus on our 8 groups here, 8 columns. And so again, 1, 2, 3, 4, 5, 6, 7, 8. And so that's the number of valence electrons. So if you say, well, how many does nitrogen have? Well, nitrogen's in the 5th column, so it must have 5 valence electrons. But also, if you did the electron configuration of nitrogen, what you'd find is that nitrogen has in the outermost energy level, the 2s2 and then 2p3. Well, if it's 2 in the S and 3 in the P, that's a total of 5. So when we do this, we would say, well, when we look at nitrogen's outermost energy, right, if we were to do our noble gas configuration, we'd do helium, and then we'd say, well, it has 2s2, 2p3. 2 plus 3 is 5. 5 valence electrons. And that would be the same thing, because we've seen that before. If you did phosphorus, you do the same thing right below it, but it would be, instead of helium, it would be neon, and instead of the 2s, it'd be 3s2, 3p3. All right? And so again, 5 valence electrons. So now we got to look at these rules. Well, how do we actually do the Lewis dot diagram? And so you simply write the symbol, right? So if we were to start with nitrogen, we'd say, well, the symbol for nitrogen is N. And now you're going to draw 1 dot for each valence electron, so 5 dots. 2 are allowed to go on the top, 2 are allowed to go on the right, 2 on the bottom, 2 on the left, for a total of 8 electrons for our 8 different groups. And so the only thing is you have to do 1 dot on each side before you can put a second dot on any side. And so with nitrogen, you do 5. I'm always going to start at the top, but you can start wherever you want. 1, 2, 3, 4, 5. And that's it. That's the Lewis dot diagram. If we were to say, well, how about fluorine? And we were to look over and say, well, fluorine's in group 7. 1, 2, 3, 4, 5, 6, 7. All right. Now, the one thing is, it doesn't matter where you put these, as long as there would be 3 sides with 2 and 1 side with 1. So fluorine could equally be, look like this over here, where instead you have 1 on the right-hand side and 2 on the left-hand side. These are the same thing. It doesn't matter where you put them. And you'll notice when we start using this that it's convenient sometimes to move around which side has the 1 and which sides have the 2. All right. The only exception to this that we need to note is, in fact, helium. Because if we look at this and we say, well, what group is helium in? It's over in group 8. But helium doesn't even have 8 electrons, so it certainly can't have 8 valence electrons because helium's electron configuration is that it has the 1s and it has 2 electrons. And that's it, it has 2. But since the s only holds 2, what we're going to do, and this is full, what we're going to do is for helium, we're going to say, well, it has 2, and we're going to put them both on the same side. This is the lone exception, all right? Everything else is going to follow our rules, but with helium, it only has room for 2, even though it's over here in column 8, but that is a full shell, all right? And because of that, you're only going to do 2, and you're going to leave them on the same side, all right? Uh, in difference to that, if you have magnesium, which is in group 2, magnesium, you do 1, 2, right? Because it's in group 2, but it could still take 6 more to make that 8. All right, so because of that, we follow the rules. Helium, the lone exception.